So we'll do some 6033 in the news. So one of the things that's in the news recently is Texas, right? And all of the blackouts in Texas. And it's, it's obviously a really challenging and difficult situation. But there are some interesting questions that, kind of come up around this situation. They also come up in a lot of things in 033, and we'll even start hinting at this today. One is just, this was really a horrible weather disaster, and it's challenging to think about how do you provision a system for what is so far, a once in a lifetime type event, right? Like, what are the trade-offs you're dealing with there? Typically, if you're provisioning a system for a really, really rare event, it might do well in that event, but it's going to be over provisioned much of the time, which you probably spent a lot of money, hired a lot of people. And there's also interesting questions, and these come up a lot in relation to Texas and its power grid, which runs differently than the power grid in a lot of the US. To think about, what incentives are there to design robust systems, and thinking, okay, had weathered this cold about 10 years ago, but like the whole disaster was like, a lot went wrong. But yes, I know it gets cold there sometimes, and it got cold there recently. But what incentives are there for people to design robust systems? What incentive is there to plan for something like this? And we'll touch a little bit on incentives today, even though we're not talking about the power grid. So this is one thing in the news lately. But then today we're going to talk about threads. And before we talk about threads, Larry, you're here. You're at the top of my screen. So we had our staff meeting this week, and Larry was just mentioning how his PhD thesis was related to the topics from last week's lecture. I always think it's cool when students get to hear from lots of people on the staff about what they work on. Larry, since it's at least tangentially related, you want to tell us for like a minute or two, just kind of what you're into and what you do and why students might be excited about it?
Well, it did. And so in the 70s, I had my thesis at NYU. We worked on the NYU Autocomputer, which was designing a massive parallel machine. And we had to have queues for many processors to put work into and pull out of. So there was the insertion and deletion in a bounded queue, exactly the problem that you talked about 2 days ago. I looked at that code for months and months and months, and it's the only time I had to look at 6 lines of code and not know if it was correct or not. And in fact, often it was incorrect. We worked on, I used something called a fetch and add, which was how to, instead of acquire and release, and we had an efficient, scalable implementation of it, but the code was really hard, and I had shivers down my spine. We ended up proving it was correct, but it's really fun and really hard. And all the questions that you asked last week about, last session about, does this happen? Can this get in there? Is there live lock or deadlock? Those are all the right questions, and it's really fun to try to prove that they're live lock free. And one of the people talked about the difference between live lock and deadlock, and live lock you can actually get out of, deadlock you can't. And I remember the last quote is someone said, well, this code is almost right. There's only one deadlock. And we said, well, you only need to have one deadlock to die. So you want it to be completely deadlock free. So yeah, I worked really hard on it. And if you want to know more about it, come see me.
So Larry, would you say that like grad school was just one big instance of Monday's lecture for you for like months, potentially years?
For 2 years.
Hey,
yes,
that's grad school. Okay, awesome. That was fun. And you all can see in the chat, actually, most of the staff do work relevant to stuff that we talk about in this class. So we'll get some little guest spots in. Hadn't really thought about this before, but Larry mentioned his thesis the other day. So I thought, let's learn about it. Okay, so we're on a quest together. We're really close to finishing the quest today, right? Goal here is to enforce modularity on a single machine, something that the client server model does for us across multiple machines. It's the operating system's job to do this. You know that the primary technique that it uses to do this is virtualization. So the operating system is interposing itself between the programs and the hardware, giving all of the programs the same interface. And so you've seen 2 of the things that we need to get this to work, right? We wanted to protect programs' memory from each other, virtual memory. We, at the same time, wanted to allow them to communicate the same way that a client and a server can communicate. That was bounded buffers last week. The last thing we have to deal with is how to get programs to share a CPU. And that's what we're going to come to today. But if you remember on Monday, which is not that long ago, with that lecture really came issues of concurrency. And, even though the bounded buffers are sort of the main topic of that lecture, it's really locks, right? Locks is what we spent a lot of time with on Monday. Locks let us create atomic actions, means that a portion of the code is going to be executed by only a single CPU at once without interruption. And, I think we all left that lecture a little bit dissatisfied with locks. We need them. We want abstractions like a bounded buffer. We want concurrency. But they're really tricky. Races, deadlock, performance issues, right? Larry spent 2 years on 6 lines of code. There's these global reasoning requirements. It's a lot, right? But also in all of this, you've seen the kernel really come into play here. It's doing the job of kind of managing all of this. It's protecting programs from each other. It's protecting itself from programs. It's the thing that's setting up the page table, handling page thoughts, controlling the bounded buffer, all of that. All right, so let's get rid of this last challenge. All right, so today, instead of assuming 1 program per CPU, we're going to allow multiple programs per CPU. The thing that's going to do that for us is threads. All right, so the same way that virtual memory virtualizes memory, bounded buffers virtualize communication links, threads virtualize processors. All right, so you see some more issues with the locks, and we're actually going to return to our bounded buffer implementation as we do this. So before we start that, why is this even a problem, right? Like, why are we worried about this? All right, well, imagine the following. Say, we have 2 programs, program 1 and program 2. They both got to run at some point, right? And maybe the operating system says, that's fine, I'll just run program 1 first. When it finishes, I'll run program 2. Whatever, that's fine. But as opposed to program 1, like, it has a bug in it, right? It gets into an infinite loop. The way I've described things to you now, it's going to go on forever and forever. Program 2 is never going to get to run. This isn't the type of, enforced modularity that we want. This isn't enforced modularity, right? So this is kind of the big thing we have in mind. How do we prevent a single program, maybe even a correctly working single program? Just how do we prevent it from halting the progress of other programs? All right, so virtualization comes into play here. We're going to create a virtual process known as a thread, all right? The job of a thread, or sort of what a thread is, it's an encapsulation of the state of a running program on a CPU, right? And so to share a CPU between multiple threads, we're going to switch threads by kind of swapping the state out, right? And the terms that we use for this are suspending and resuming, right? So if you have 2 threads, say A and B, maybe A is running. At some point, something is going to jump in and say, okay, I'm going to suspend thread A, resume thread B. Now thread B is running. And then later, suspend thread B, resume thread A. All right. Now, you might be thinking of this so far as to say, like, okay, well, we're sort of going to put like 1 program per thread, right? That is actually a fine way to think about things for this lecture. That's not going to be a problematic, like, mental model to have. It is entirely possible, though, to have a single program that's using multiple threads, to have a multi-threaded program. So it might be a little bit more correct for me to talk to you about a thread encapsulating the state of a particular computation rather than a particular program, but program's going to work fine for us. All right. So the words we use here are suspend and resume. So we're going to get this to work. All right. I'm going to have some code for you on the slides in just a second. But there are 2, there's kind of 2 questions that we have to solve, both of which we will solve today. This is going to be a successful day for us in O33. Okay, we are going to solve this problem. Since the job of a thread is to encapsulate something about a program state, we have to think about, well, what does that mean? All right, so a program state is the value of all of its registers, the stack, the program counter, all of the program's memory, right, heap stack, all of that, which is actually pretty easily captured with the page table register because it points to the right page table, and that tells us everything we need to know. And then the second question, which is really going to be the driver for this lecture, is, well, okay, so we can suspend and resume a thread, but when do we do it, right? The short answer is periodically. In the most ideal case, we suspend a program when it's busy waiting for something to happen, right? So since we're going to spend a lot of time on the second issue, let me give you an example right away. So first of all, you might remember this code from Monday. This is a great time for me to mention that I did have a typo in the sort of the last piece of code that you saw on Monday, which was very quickly pointed out by someone on Piazza. So thank you for that. I had the condition on the while loop flipped around. And knowing that Larry spent 2 years looking at the same 6 lines of code, I now feel better that I let that typo get through. But so this should be correct. And so this is the code that we saw last week. And like, let's think about it again. So what this code is doing, sending into a bounded buffer. If we get the lock and there's space in the buffer, we put the message in, we release the lock, everything is amazing. If we get the lock and we find that the buffer is full, this is okay. You release the lock and then try to acquire it again at a later point. Right, and the whole goal here is to remember that, you know, in between these lines, in between this release and acquire, the kernel could have another program jump in, right? Hopefully one that is receiving a message, it's actually going to take a message out of the buffer, and then we return, we get the lock, there's space in the buffer, we can go ahead, right? But a problem is, of course, that might not happen, right? You know, if this sending call were to just like release the lock and then get it right away, the buffer's still full. Right? And it's just kind of going to keep releasing and acquiring and releasing and acquiring. This is a great example of code that is waiting for something else to happen, right? At that point in the code, it's waiting for some other program to receive a message, all right? So, you know, how does the kernel know that, right? Like how does the kernel infer that, oh, this thread is waiting for something to happen? It'd be a great time to like let something else come in, right? The way it's going to know is we're going to tell it, right? So we're going to have this one line called yield, right? So yield's job is to suspend the current thread, resume another thread, which it could possibly come back to this thread, but hopefully there's other threads hanging out, right? And then eventually we'll come back to this thread. So our first job today is to understand exactly what that means, right? What does it mean to suspend a thread? What does it mean to resume another thread? How do we get this to work, right? So we're going to spend a lot of time figuring out yield. So bounded buffer code goes away for a second, it's going to come back. All right, but let's think about yield. All right, so your textbook describes yield as among the most mysterious code in an operating system. So today we will try to demystify this. All right, at a high level, yield's got to do 3 things. It's got to suspend whatever thread is running, choose a new thread to run, and then resume the new thread. So to get this to work, we're going to need a few data structures. So on these slides, you're going to see data structures over on the left, just so you remember what they do. And we will build up code for yield on the right. All right, so first things first, we are going to want everything that happens in yield to happen as one atomic action. All right, so we're going to have a lock protecting this code. I used T-lock for threads lock. That's the term I have chosen. All right, so here's our first thing is just a lock. Now, what do we need to keep track of, right? What do we need to keep track of in order to do the suspending and resuming and all of this other stuff? All right, a couple of data structures. Most of them are basically just tables though, right? No weird trees, no linked list, just kind of tables, right? So one of the things we're going to use threads, the threads table. So this is going to contain information about each thread. And I will tell you some of the information now. We're going to end up adding to this, so you'll see this happening. All right, so for each thread, we're going to store a few things. One is the thread's state. Right now, at this point in your life, threads can be runnable or they can be running, right? Running means this thread is actively running. Runnable means it's able to be run, but is not currently running, right? We're going to have a stack pointer, which I'll abbreviate SP in the code. We're going to have a page table register, PTR in the code. All right, so that's what we're going to work with first. So that you can see this in action, let me show you the first part of yield. All right, the action, the operation of suspending the currently running thread. All right, what this is going to do, it's going to figure out the ID of the thread that's currently running on the CPU. We'll make that a little bit less pseudocode in a second. It's going to set that thread's state to runnable because it's no longer running. It's ready to be run, but it's not running. And it's going to save the stack pointer and the page table register. All right. Well, let's talk about this first. So why? That's like not that much, right? Why aren't we doing anything with additional memory? Because it's all taken care of by virtual memory. We have a pointer to the page table register. We're good to go. All right. Why aren't we storing any other additional registers here? Right. Any additional registers that the thread is using are going to be stored on the stack. So saving the stack pointer effectively takes care of that. Why aren't we storing the program counter? It's a very good question. I am assuming that the calling function here is explicitly pushing that to the stack. And so it's captured by the stack pointer. If you don't like that design, that's fine. You can save the program counter separately. This design I like for kind of teaching purposes. Once you understand this, you could implement this in slightly different ways. All right, there's a lot of details that you could change a little bit. All right, so this is really, at this point, this is all we need to know about a thread, right? And all we need to save. Right. In the interest of getting you closer to real code and less pseudocode, we will need a way to get the ID of the current thread. We're going to get that in another table, right? Of a table CPUs that keeps track of the ID of the thread currently running on each CPU. You can assume the thread IDs in this example, they're not fancy. They're just numbers. They're like every time I make a new thread, I just increment the number. Okay, so nothing fancy there. So we have suspended the new thread, right? If this seems a little bit iffy to you, resuming the new thread, I think will kind of bring this together. But before we resume a new thread, we need to actually choose one to run. At this point of the lecture, we're going to adopt a really simple strategy. What we're going to do, we're just going to look through the threads table and find one that's runnable, right? So find a thread that's not running currently, but is able to be run. All right, so skip any that might be running on other CPUs, right? Find one that's runnable, right? Nothing fancy, just cycling through until we find a runnable thread, right? This is not how most thread schedulers work. We're gonna talk about that at the very end of class, but this is gonna work fine for us now. But notice one thing, all right? Anytime, like, whenever there's a loop, right? There's a concern of, was that loop going to terminate? Right? It would definitely be a problem if your kernel got into an infinite loop. That would just, things would be bad, right? But notice this, if nothing else, if there are no other runnable threads out there, we're gonna end up coming back to the current thread, right? The one that we sort of just suspended. And maybe that feels a little bit silly from a performance standpoint, but this loop is guaranteed to terminate. I'm bringing that up now. If you're on top of things, 15, 20 minutes from now, I'm going to ask you a similar question. It's going to have a different answer. All right, but for now, that loop is going to terminate. So the last thing we need to do is resume the thread. Resuming the thread is in some ways the reverse of suspending it. All right, take this new thread, the one that we've chosen in the second part there, get its stack pointer, get its page table register, right? Set the real stack pointer and page table register to those things, set its status as running, keep track of what thread we're currently running on the CPU, and then you're done. Right? So a totally valid question at this point is like, is that it? Right? Like, did this really work? Right? So it is worth like thinking through this code really carefully. But notice that what's going to happen when we exit this code, right? Before, the stack pointer and the page table registers were pointing to the stack pointer and page table registers of a particular thread, right? In this code, we switched that. Now they're pointing to somewhere new. So when this code returns, right, when we're out of yield, now we're in a different place, right? Where now the computer will continue to execute things. It's going to be executing things of a different thread. I think that this is really nice. I think that, you know, it feels like there should be a whole bunch of stuff saved and a whole bunch of stuff switching around, but you have a lot of abstractions in an operating system that should make this relatively clean compared to what you might imagine it's like, right? And to bring us back full circle, now that this code is filled in, you can see exactly what TLOC is protecting here. It's allowing us to atomically set a thread's state, its stack pointer, page table register. So letting us atomically find a runnable thread and mark it as running, right? So this is what is going on in yield. Now, let's go back. Let's go back to send. All right, so send called yield. Here's what happens with yield. A question we can ask ourselves now. Let's see, I think I made a poll for this. Let's do the poll. That's always exciting for me. All right, so, okay. In this question, which again, totally anonymous, not gonna share the results, it's just a thinking question. We've got a thread that calls send, this version of send on this slide right here with this version of yield. Buffer is full, so it yields. There's no other threads. What's gonna happen? I'll let you all think about this while I drink some water.
Hey, Katrina, you also have a question on the chat.
I see that. Does anyone on the staff want to jump in? I don't know if I'm sure of the answer to this.
I'm not the expert. My feeling is it doesn't matter. Or maybe Larry should answer.
Harry, I appreciated though that you thought I would be the expert. That's bold. That is my sense.
But I don't think it actually matters.
I agree, but we'll try to come up with a more detailed answer after the lecture. All right, 5 more seconds. And if you don't have time to put an answer, like, we're fine. I'm not collecting like strong data on this poll. Okay. So the reason I asked you this question, all right, so what's going to happen, right? So our thread calls send, finds the buffer full, releases the lock, and yields. All right, you have the code for yield. Yield's going to go through all of the other threads, and there aren't any, right? I told you there aren't any. It's going to end up choosing this thread again. Okay, so we'll acquire the lock, which presumably we'll get, there's nothing else going on here. The buffer is still full. We're going to release, we're going to yield again. It's just going to kind of keep going. And there's nothing incorrect about that, but it's sort of dissatisfying, right? And in a way, it's dissatisfying because it would be really nice to have a way to do something like this. It'd be really nice if that sending code could say, look, I'm trying to send a message and the buffer is full. I'm going to yield the processor because I can't make any progress. And it doesn't make any sense to even come back to this code until there is room in the buffer, right? It would be great to try to indicate that to the kernel. And good news for all of you, we can do that, all right? Most operating systems provide an abstraction for this. So that's the second thing we're going to talk about today. Subtraction is known as a condition variable. All right, so we'll stick with this code. I'm going to show you how this works in a second. All right, so condition variables, I'm going to let threads wait for events, conditions, and then get notified when they occur. So you can wait on a condition, you can be notified of it occurring. This now explains one of the songs you were listening to before a lecture. So I'm going to put receive code up next to this. I'll just go ahead and put it up now. So I've added 2 additional things that we haven't seen before. All right, they're really just flags. All right, a condition variable is basically just a flag in some ways. And so we have these 2 events, has space and has message. Send waits for the condition has space to occur, right? And then once a message is sent, notifies the operating system that bounded buffer now has a message, right? On the other side, receive is going to wait for the buffer to have a message, and once it's read a message, notify that, okay, now the buffer has space, right? We're going to implement this. We are going to get this to work in just a second, but there is actually a problem with the code the way that I've sent it to you so far. All right, so here is the problem. Let's see, okay, we'll okay, Karen, you get to be the sender. Try to embody the sender for us all. This is Karen. Howie, you get to be the receiver. Okay, so perform your best receiver over Zoom. And so imagine this, okay? So Karen is a sender, goes to send a message, finds that the buffer is full, all right? That's fine. Finds that the buffer is full and releases the lock and gets interrupted here, all right? So I, the kernel, interrupt. And I say, Karen, no more, you stop, right? So Karen has released the lock. That's where she is, all right? And now I choose to let Howie execute, all right? So Howie goes ahead.
Okay.
Calls receive, gets the lock, finds that, oh, actually, out is less than in, there finds that there is a message here, goes ahead, reads it, notifies, calls notify. Howie just executes everything. All right, so in particular, he executes this line. In this example, maybe there's some other threads waiting for the notify, but Karen was not waiting for it. She hadn't registered that she was waiting for it yet. All right, and so now, okay, Howie's done, we switch back to Karen. All right, Karen goes ahead and continues to execute, right? In particular, he says, okay, now I'm waiting for this buffer to have space, so I'm gonna yield, right? Waiting for that. The problem is that Howie's notification, which would have been extremely relevant to Karen, she didn't get, right? This is known as a lost notify problem, right? So Howie notified everyone correctly. It's just that Karen hadn't said, I'm waiting for this yet, right? What that wait is doing is basically registering a thread as waiting for a particular event. And Karen hadn't been able to do that yet. So we're gonna solve this problem, right? We're gonna solve this problem by changing how we use condition variables just a little bit, right? That's why I didn't give you like a super complicated API yet. And that's why we haven't looked at the code for wait and notify, because it's gonna work slightly differently. All right, so we'll stick with send for a second, right? Here's what our condition variable API is gonna look like. Still wait and notify, but wait is gonna take an argument. The second argument that it's gonna take is a particular lock. Right, so the job of wait is going to be to yield the processor, release that lock, wait to be notified of this condition variable, reacquire the lock, and then go about its business. Right, so we now have another job. We need to understand how wait and notify work. We also want to understand, like, where is yield in all of this, right? I've said that, okay, wait is going to yield the processor. Does that mean it's just going to call yield? Is it going to do something different? Let's find out together, right? Who knows? Who knows? We'll find out together. Okay, so first we're going to look at wait, then I'll bring notify back in, right? Now, data structures on the left, same ones you saw before, right? We are going to use them again. We're going to add to them a little bit, but same setup as before. Thinking about what wait should do, we are going to want all of this to be an atomic action, right? So we're going to use our lock again, right, to wrap that. And if you're reading this code, if you're like really, I don't know, you got the slides early, you're studying all this, like this code is not going to work right away. It's what, it's 2:35. I would say give us 10 minutes or so before we have a version that works fully, right? But let's start here. So we've got the lock, right? We are waiting. The first job of wait is to release that argument, all right? Release the lock that is part of this argument. So in our bounded buffer example, that would be the lock on the bounded buffer. Release it, it's gonna do some stuff. It's gonna get the lock back at the end so that the calling code still properly has that, right? What it's going to do here is it's going to say, okay, this thread is now waiting on this particular condition variable. So using the same data structures we had before, we just need to add one little field, right? We're going to add that we're keeping track of the condition variable that the thread is waiting on. You can also see now that threads can be in one of 3 states, right? They can be running, like actively running. They can be waiting, which means they are not going to do anything until they're notified, or they can be runnable, right? Which means they're ready to go, but they're not running right this second, right? And then the only other thing wait has to do is call yield. For right now, I've given this a different name. The reason I've given it a different name is because it's going to be slightly different from yield. But right now you can assume it's basically doing the same thing. I called it yield wait because it's the version of yield called by wait. There's nothing more complicated for that, right? We're going to go into the code of yield wait because that is where all of the excitement happens here. But before we do that, I think it will help clear up some mystery of this process for you to see what notify does. Okay, so we're going to hold off on yield wait. Here's what's going on in notify. Notify actually has a much more straightforward job than wait does, right? It's going to say, hey, okay, great. We are notifying all threads, right, that are waiting on this particular condition. So I'm just going to go through all the threads, find the ones that are waiting on this condition, and set them to runnable, right? Because the condition that they're waiting for has happened. They're ready to be run now. They are not running, but they're ready to be run, right? So the main thing that notify is doing is setting threads waiting on a particular condition to be runnable, right? That's going to become very important in a moment, right? But so wait and notify. Notify is looking good, right? We're not going to have to worry very much more about what notify does. We are going to have to worry a little bit about what wait does. Okay, so we're going to come back to wait. I'm putting it on the left because the reason we're coming back to wait is because we need to come back to yield wait and understand why this would have to be different. All right, so to convince you that it's different, I'm going to start by just copying the code from yield. All right, this code that's in here now, it's exactly what you saw in yield. We suspend the running thread in the exact same way. We choose a new thread to run in the exact same way. We resume a new thread in the exact same way. And immediately we run into a problem. All right. I'll give you don't have to put it in the chat. You don't have to say anything. I'm gonna give you like 15 seconds. What do you think the problem is? Okay, let's see if you got it. First problem is just deadlock, right? Wait is holding this lock and then it's calling yield wait, which is gonna try to acquire the lock. This is not exactly what we wanted. And you know what? Normally locking issues are so challenging and such a headache to solve. This one, you know what? Just delete it. All right. Yes, we're making a function call here, but this function call is already protected with inside the bounds of the lock. So we're going to go ahead and just delete that. All right, so that's great. Problem 1 is solved. Right now, problem 2. Right, and this is just a logical issue with us pulling the yield code in here. Notice that, okay, as part of wait, I'm setting the thread state to be waiting. All right. But then the first thing we did in yield was set its state to be runnable, which made sense before. It just doesn't make sense now. That's not actually what we want. We don't want to overwrite and say, okay, well, this thread state is runnable. It's not. It should be waiting. We've already set it to waiting. So again, we'll just delete that. Right. So far, we're dealing with essentially yield, but we've deleted some extraneous things from the code. All right. Now things get trickier, right? The reason things get trickier is because of this loop, right? The only loop we have to deal with here. We talked about this loop before, right? I told you to pay close attention because I was going to ask you about it again. It's happening right now to you. All right. Before I ask you a question, is this loop guaranteed to terminate? And we all said yes, it's guaranteed to terminate because if nothing else, it's just going to go back to the thread that we just suspended. What about now? Given the code on the screen, is this loop guaranteed every single time to terminate?
No.
Yeah, no. You can also use context clues. I would not have hyped you up so much for a question whose answer was just yes. It's not guaranteed to terminate. We don't know that there's a runnable thread, right? Oh man, like this is the big issue. Those other first two problems, they were fine. We just deleted some code. This is more complicated, but you've seen this type of problem. You've seen this type of problem on Monday, right? On Monday, we had this issue where our send code was working great, but we held this lock and it meant that no one could jump in and receive a message and let us make progress, right? We actually have a similar thing going on here, all right? The only way, let's again, imagine bounded buffer. Bounded buffer is a great application for this code, right? We have sent into the buffer. We're all sending, okay? Every single one of you is a sender right now. Howie is our only receiver. We are all sending. We all find the buffer full. We're all waiting, and like Howie's trying to receive, but he needs to be notified that there's messages and all sorts of stuff. All right, so we're going to do a similar thing. All right, we're going to give up this lock in the middle and then reacquire it so that other threads can jump in and actually do things. Right, in particular, so that threads can be notified that there is an event that they've been waiting on that's happening. All right, get some of their states back to runnable, actually let threads jump in here and do the work. Right, this is our biggest issue here. This is I would say the biggest difference between yield and yield wait. Lest you think we were done. This code on its own is actually not quite finished yet. Right, and the reason it's not quite finished, right? This is exhausting, right? Like, imagine Larry doing this for 2 straight years. We're in minute 38, and it's so tiring, right? We're gonna get there with one more round. One other challenge we have here, we have our stack pointer, like capital SP, pointing to the original thread's stack. Call it thread A. Between this release and acquire, all right, in this line here, another CPU could jump in, could run that thread, all right? This means that we would have 2 CPUs and their stack pointer pointing to threads A stack. And this is right before stack corruption, right? When I learned about this type of problem, for a long time, I was like, really? Like how often could that really happen? Like how big of a problem is this? There are early versions of different operating systems that totally got this wrong and really did lead to a bug where the stack would get corrupted. Especially given thread schedulers that are usually much more complicated than this loop that we're running here. It is an issue, all right? It is an issue that in our code, we can solve relatively swiftly, all right? We're going to just sort of have our stack pointer point to somewhere else, right, instead of into thread A's stack. And this is gonna get us where we want to go, all right? So this is the last thing to solve. It's a pretty subtle issue. Again, like I said, to me, the big difference is in here, in understanding that we need to release that lock to let other threads jump in and do their job. All right, so we've done much work on this, so much work on this. Let me give you all a question. Let me give you all poll number 2. All right, all of this work, we know so much about yield, so much about wait, so much about notifying. It would be really bad if threads just never called wait or yield. right? So this is an opinion poll. There's going to be a real answer, but I haven't told you the answer yet. Suppose threads don't call yield or wait. It means that one thread could potentially keep the CPU forever, right? What do you think stops that from happening, right? What prevents, say, Howie's program from just never calling yield, never calling wait? We'll do 10 more seconds. I appreciate the people who are choosing the second option. I would like to live in a world where the answer is the second option. All right. So indeed, this is going to be problematic. All right. There's nothing, what could we do to require programmers to call yield, right? What law could we enact that would force Howie to put yield in his code, right? And there's nothing. And this is bad. If this doesn't happen, all of our enforced modularity falls apart. Okay, but it's okay. Preemption. Preemption is the answer. All right, the operating system is going to jump in. It's going to use special hardware, a timer, to basically periodically generate an interrupt. And that interrupt handler will just forcibly call yield. All right, so if you're not calling yield, the kernel is going to make you yield. This yield goes the same way as before, but of course there's an issue, right? You can imagine that we might get ourselves into trouble if, say, Karen's code is calling yield, and at the same time it's calling yield, this timer interrupt fires and also calls yield, and we're trying to get locks, and it's very bad, right? Trying to do 2 calls to yield at once, right? There is a solution, right? The solution is that there is a hardware mechanism to disable this particular interrupt. And the reason this matters, it's not because we're that interested in you knowing the finer details of this hardware mechanism. Even this timer interrupt code, I want you to understand what it looks like. It's not something we're going to get really into. The reason this matters is because it's so similar to every other thing you've seen, right? Remember that to get locks to work, we needed hardware support. We needed that atomic exchange operation. To get virtual memory to work, we needed hardware support. We needed a memory management unit, and we needed the physical address of the page table registers. To get DNS to work, we needed the IP address of the root servers, right? We need this little piece of information or this little piece of hardware to bootstrap the entire system for us. Right? So this happens over and over. All right, now we have time. I'm so excited. I planned for this. We don't magically have time. I knew that there would be 5 minutes left at this point. I want to talk a little bit about scheduling. We're not going to get into it in detail today, right? But I wanted to start to inspire questions in you that we're going to answer later. Also in the chat, I know exactly how long every lecture is going to take and where we should be at every point. I'm extremely good at my job. All right, so thread scheduling. We did something really, really simple here. There's other things we could have done. We could have done something like first come, first serve. The thread that yields first gets to go first. All right. We could have done something like priority scheduling. Have a notion of like how important a thread is. Threads that need to finish sooner get scheduled first. We could have done something like shortest remaining time first. So if we had a way to estimate how much longer a thread would be running, we could try to get those like short ones out of the way first. We could have done something like a type of round robin scheme where we just say, okay, each thread gets a particular amount of time. We just go round robin. As the thread's finished, that's fine. They're out of the round and new threads come in, right? So why talk about this now? How threads are scheduled has a huge impact on performance, but also fairness. And you've been in this class long enough that you can start to have thoughts about whether things are fair and how we would even measure that in a system, right? There is no best scheduling algorithm. I picked these 4 as examples because they're used, like they're common. I picked them in part because they're going to come up in a couple weeks when we talk about networks. So you can schedule threads in an operating system. You can also schedule packets out of a queue on a network, and that's the context we're going to see these in, right? But this is going to bring up bigger questions, right? So for instance, the question of priority scheduling. How do you decide what threads are the most important? Or on a network, how do you decide what traffic is the most important, right? Is there an objective measure of priority there? Is it whatever company is paying the ISP the most money, right? How do you deal with this, right? How do we even think about this in systems? And how do we do something that's gonna, make performance kind of work for everyone? I can tell you that most thread schedulers, they're super complicated. They're usually built around things like this, but often have some kind of manual tweaks that tend to just give us good performance empirically. And again, we're not going to dive into any of these yet, right? You don't need to know anything more about these scheduling algorithms than what's on the slide. It's like you don't even really need to know what's on the slide yet. Just know that there are many, that there's no best scheduling algorithm, but that it really matters, right? Performance is affected, fairness is affected. Okay, so where are you now? We did it, right? We have enforced modularity on a single machine, right? And so what have you seen? I think it's been, at least for me, the last two lectures here are sort of really the big ideas, right? Because we've seen locks and we've seen threads, and they're interesting to talk about from a design point of view, right? So on the one hand, we needed locks to get our bounded buffer to work. We need our threads to share a processor. But now there's all these like modularity issues, right? Locks required global reasoning. It's really challenging. So there are ways to bring modularity back to this problem. One of the ways to bring modularity back to threads is to use layering, which effectively gives you a more modular way to organize all of your threads. There's actually a section in your book about it. I'll put the section in the notes in case you want to look at it. There are still issues to contend with there. And then in terms of locks, there are ways to bring a more systematic approach to locks. We are going to talk about that. We won't get there until April. I'm looking at the calendar until April-ish, but we will come back to locks, right? And again, you've seen this theme through all of these techniques. When you've seen virtualization, all of these things look different. They're all applications of virtualization. And you've also seen this theme of, to truly enforce modularity, we needed support from the kernel and we needed support from hardware, right? So at this point, we actually have, as far as we're going to, we have successfully enforced modularity in a single machine within an operating system. There's one more lecture left in operating systems. And what we're going to talk about there is, the kernel code itself. Is there modularity within the kernel code, and why or why not? We're also going to talk about how you might run multiple instances of an operating system on one physical machine, which is a very common thing to do these days. And we're also going to wrap up some performance issues. So I have touched on performance in every single operating systems lecture, also touched on it in the majority of recitations. But we're going to summarize it for you on Tuesday, not on Monday. Tuesday is a Monday next week. And it'll be a nice segue into networking, right? So Tuesday we wrap up operating systems. Wednesday we watch networking. Wednesday, that means we probably watch my favorite YouTube video if I can fit it in, okay? But come on Tuesday as well. All right, so I'll hang out.